In this video, we will find the intersection of two surfaces. Now in general, the intersection of two surfaces is going to be a curve. And so we want to represent that curve parametrically, that is, with a vector function. So there's more than one way to do this, and in this example, the equation of both surfaces are represented as graphs. That is, they're both solved for one of the variables, in this case z. Now this isn't always possible, so this technique won't apply to every example, but in this example we can solve both equations for z, and they're already given to us that way. So the idea is to set them equal to each other. Since they're both equal to z, they're equal to each other, so we get 1 plus y equals the square root of x squared plus y squared for the points on the intersection. Now let's mess around with this equation a little bit. So first, let's square both sides to get rid of that square root sign. So 1 plus y squared is x squared plus y squared, which, if we expand the left-hand side, is 1 plus 2y plus y squared. We have y squared on both sides, so we can cancel them. And let's solve for y. So y is x squared minus 1 over 2. So this is telling us that along the intersection of these two surfaces, which is some curve, the points on that curve have this relationship between their x and y coordinates. That y is equal to x squared minus 1 over 2. Now since y depends on x here, that means if we know the x coordinate of a point, we uniquely know the y coordinate too. And from the two equations we were given at the beginning, we can then also determine z, knowing x. So what we've discovered here is that everything depends on x. If we know x, we also know y and z. So if we want to parameterize this curve of intersection, we can choose our parameter, which we usually call t, to just be the same thing as the x coordinate. That is, call our function x of t to just be t itself. And now the y component of our vector function will just be given by what we got over here on the left in the box. Y is x squared minus 1 over 2. But since x is the same thing as t, this is just t squared minus 1 over 2. Similarly, the z coordinate is very easy to figure out. Just use either of the two equations from the top that we were given at the beginning. The second one is a little simpler looking, so let's use that. Z is equal to 1 plus y. So it's 1 plus, and y is written right above. Y is t squared minus 1 over 2. So to summarize and put all three of these together, we could just write it like this. We could parameterize the curve as a vector function using these three functions that we wrote here as the components. So t squared minus 1 over 2, and 1 plus t squared minus 1 over 2. And that is a parameterization of the curve of intersection of these two surfaces.